Okay, now let us start the new lesson. Oh, sorry. There was something I want to talk about. So this is a theorem, another theorem. I just want to explain it a little bit, and then I really want you to sit down and do it yourself because it's very easy. So this is categorizing all cyclic groups. Okay. So Cayley's theorem told us that there is only one type of group that we are interested in, and that's the group of permutations, essentially. But we also have some theorems like Cayley's theorem for cyclic groups. So let me start only part B, for example. Here you see every cyclic group of infinite order is always isomorphic to Z. Okay, as simple as that. Okay, is that understandable? I want you to help me to prove it, because the proof is very simple, even though it is claiming a big thing, because it's telling you that every cyclic group that is of infinite order, it's always isomorphic to Z. So if you know Z, you already know every cyclic group of infinite order. Okay, and by the way, when I say Z and I don't emphasize the operation, what the operation is? Addition. Okay, so can you tell me why? Is that understandable? It means that if you, so G is cyclic, and we know order of G is infinite. The claim is that Z is isomorphic to G. Okay? This is simple. So it means that if you know that you have a cyclic group of infinite order, you can throw it in the basket, in the bin, and just work with Z. Okay, so can you tell me why? Because this is at the intuitive level. In algebra, it is very important to develop some kind of instinct, the simplest possible one, and then go for it, at least for the first try. So if I want to prove that Z is isomorphic to G, what do I need to establish? I need to establish a one-to-one correspondence between this abstract group that I don't know anything about, except that I know it is of infinite order and it is cyclic, with the group of Z that I really know it very well. So in principle, if you want to go to a scratch paper and work it out, you ask yourself, I need a function from Z, for example, to G, which is 1 to 1 and on 2, such that what happens, can you tell me? Such that it respects the binary operations. How should I write it down? F on AB. A and B should come from Z, so we usually denote them with MN. And this binary operation should be which one? I told you before. Of course, you can write MN, but here MN means M binary operation with N on the group binary operation here. So it is plus. Equal to what? Fm multiplied, because this is just a typical group. Okay? Fn. So this is the way you have to think in a scratch paper. If you can come up with this function, which is bijective and respects this rule, you are done. And think about the most natural one. So this means that on the one hand, you have Z, element is N, a typical element is N, and you have G. But what is G now? G is cyclic. When you say G is cyclic, it has a generator. So when you say G is cyclic, it means that G is group generated by a generator A. Yes? And do you remember what is the form of this? What is the definition? The definition was A to some power, any power M, so that M belongs to Z. That was the definition of the cyclic group. Yes? Okay, so this means that the elements of G are powers of A. So for example, you have A to power 0, which is identity, A to power 1, A to power 2, and A to power minus 1, A to power minus 2, etc. Okay? And one of them is what? One of them is a to power n, which is that n. So it tells me this should be a natural place to start. Yes? So when you do this in a scratch paper, you get a feeling of what is your bijection, and you say that claim. So can you fill up my claim? Claim the function f from z to g defined by, I am waiting for you, defined by what?
f of a.
F of n,
Yes.
Equals a to the power.
a to power n. The function this defined by is an isomorphism. Yes? So you develop some kind of feeling in a scratch paper, and then you claim something, and then you prove your claim. Yes? But proving the claim is on you, because it's extremely simple exercise. Yes? If I want to prove, for example, let me just do the bijectivity. Sorry, injectivity. Why this is injective? I will pick m and n in z such that f of m is equal to f of n, and I ask myself, does this guarantee that m is equal to n or not? If it guarantees, it is injective. But do you think it guarantees? Let us check. I start from f of m equals to f of n. So this means that a to power m is equal to a to power n. But do you remember we had this theorem before, that if a is of infinite order, this happens if and only if the exponents are the same. Yes? That's it. That's bijectivity. This is injectivity. But based on a theorem we had. Do you remember we had two theorems? If a is of finite order or not. If it is of infinite order, this is always established. If it was of finite order, do you remember what was the rule? I just want to remind you. If I know that a to power m equals to a to power n, but the order of a is finite, so let me write it. So what is this happens if and only if, do you remember? Yes?
One of them divides the other.
No.
M
The
divides
order of a divides the difference. Yeah, we had this before. But here I am talking about this. So this is why the first one is a little bit harder to do. To inject it. Okay, but you can complete it yourself. Yeah, please do that, because then you will understand. But the important thing, if you want to be a good mathematician, you should develop some kind of feeling so that you know where to start from. Okay? Is that clear? Yes? Yes or no? Okay. So let us now go to the new lesson. So here this remark is also good to know. Any two cyclic groups of the same order, including infinite group, are isomorphic. And you say why? If I give you two cyclic groups, G1 and G2, both of them are infinite and both of them are cyclic. Why they are isomorphic to one another?
Because isn't the function just go to the generators somehow?
Somehow, I don't want you to start from scratch. I want you to think like a mathematician.
Because that's the function with the generator for one of them when one is cyclic. So shouldn't it just be a power m equals a power n if m?
Yeah, you are starting from scratch. I mean, the mindset of a mathematician, if I can announce it. So this is the mindset of a mathematician. If I want to put this eraser from here on the table, I take it and put it on the table. And the question is that if I have it on top of the ceiling and I want to put it here, what do? Mathematicians don't say that I will take it and put it on the floor. Mathematicians say that I will take it and put it here and solve the problem as before. Yes? So this is the mindset of a mathematician. What you said is starting putting this from the ceiling to the floor directly. That's not wrong, but you should have changed your mindset if you want to be a good mathematician. So if you want, yes?
Cyclic groups are permutations, are they not?
No, cyclic groups are the ones which are, this is the definition of a cyclic group. A cyclic group is a group with a generator. So it means that a cyclic group is a group of this form for some A. That was the cyclic group we did before. Okay? So this means that if I want to say why they are isomorphic, I would say that G1, according to this theorem, is isomorphic to Z. G2 is also isomorphic to Z. Then they have to be isomorphic to one another. This is exactly like this example I mentioned. But this needs a very important thing. Why, if two groups are isomorphic with one group, they have to be isomorphic to one another? By the way, let me ask you some intuition. Is any group isomorphic to itself?
Yeah.
Yes. Why? Yes.
Because the
So you need to give me the yes.
identity function.
The identity function plays the role of the isomorphism. If a group G is isomorphic, if G1 is isomorphic to G2, is G2 isomorphic to G1?
Yes.
Why?
Inverse
Additivity.
Bijectivity and
inverse function.
inverse function. Okay. And now if G1 is isomorphic to G2 and G2 is isomorphic to G3, is G1 isomorphic to G3?
Yes.
Yes. So the first, let us say that the first one is F, isomorphism. The second one is G. So which one makes an isomorphism between G1 and G3?
The composition. Of
The composition. Yes. So these are intuitive things that you have to actually sit down and prove. But these were very moral. That was the proof. We did it orally. Okay. So now let us go to the very important lesson, but very simple one, hopefully. Partitions and equivalence relations. And now if this is done, you can do the last homework. So every homework problem can be done now. So partitions and equivalence relations. So let me do it on the board a little bit faster. The first thing I want to remind you is the Cartesian product. I haven't have any slides for them because we don't need it that much, but I just want you to know, if you give me two sets, A and B, you can union them, you can intersect them, you can find the difference between them, but there is also another operation. You can multiply them like this, and that is called the Cartesian product of A by B, from left to right. Do you remember what was the definition?
Yes, the ordered pair.
Yes, it is the set of all possible ordered pairs so that the first component is coming from the set on the left and the second component is coming from the set on the right. Yes, that's called the Cartesian product of A. Okay, but here in this lesson, we don't like it that much. We are not working with these kinds of Cartesian products. We are only working with Cartesian products for which the left set and the right set are both the same. Okay, so it doesn't matter. That's a particular case. So that's why if you go to my slides, okay. Yes, let me explain it here for you. If I give you A and B, so from now on, let us only think about these two. So for example, if I give you A to be 1, 2, and 3, can you tell me what is A cross A? By the way, sometimes people write it as A squared. A set squared means this. It doesn't mean, for example, if I give you this set and I ask you A squared, don't write 1, 4, and 9. A squared is a shorthand notation for A cross A. The cross here is the Cartesian product. Yes? So, what does it mean? It means that this is a set of all possible ordered pairs whose first component is coming from A, but here the right component is also coming from A. So, but you have to list all of it. So what is that? Do you agree? One is one of them. 1 and 2. 1 and 3. 2 and 1. 2 and 2. 2 and 3. And then you have 3 and 1. 3 and 2. And 3 and 3. This is A squared. Or A times A. But now when I say write a relation from A to A relation from on A means, this is the definition, means a subset. So for the time being, we don't have anything with groups this lesson, no groups. Okay, so a subset of A squared, which is defined to be A cross A. That is the definition of a relation. Yes? So for making a relation, what ingredients you need? You need a set, and in principle, you imagine a squared and write any subset of a squared. What you write is called a relation. Is that clear? So for example, let me see what I have written here for you. So this example number 1, I have given you A. Write 2 relations on A. Can you write it for me? So this is exactly this set. I want you to write 2 relations on A. For example, let me write relation number 1. So can you help me write a relation on A? So in principle, you have to imagine A times A, which we did it explicitly, and pick any number of elements you write a subset. For example, can I write 1 and 2 and close it? Do you think it's a relation? Yes, because it's a subset. For example, is this a relation? I don't know, 1, 1, 2, 2, 3, 3. Is this a relation? Yes. Okay, I have asked you, what is the smallest relation?
Is it empty set?
The empty set.
Always empty set.
Yes, it's the empty set. So because empty set is a subset of every set. So the empty set is the smallest relation. And what is the biggest relation here? A squared itself. That's the biggest relation. How many relations I can write on A?
2 to the power of the number of a squared. So
Yes. Number of A squared is, A has 3 elements. So A squared will have 3 times 3, 9 elements. And the number of subsets is 2 to the power 9 is what? 512. So there are 512 relations that I can write. The smallest one is the empty set. The largest one is A squared itself. A very simple concept, yes? So you deserve it to have a simple lesson. Okay, so let us now go to the next one. Now this is a checkpoint. I want you to just do it yourself. These are very, very simple ones. But remark 2 is a good one. This is some kind of notation. From now on, we want to use it. So you see, let me explain this notation here. So here, in principle, in the language of set theory, here I can write this element belongs to R1. Do you agree? This is the standard notation. But from now on, when we are dealing with relations, I will write it as 1. I put the name R1 in the middle and then write 2. So these are the same. I am defining this notation for you. And I am reading it as 1 is related to 2. Or 1 is in relation with 2.
So that means that
This means exactly this.
that means it's in the relation.
Yes. That's the meaning. But this is the notation we will use here. Okay, let us go to the next one. This is a little bit more tricky, and I really want you to understand it. Okay. Can you read it yourself now, and then help me to do it? Okay. So could you understand what is going on? You will not see these kinds of exercises in the book, but I really want you to understand what you are doing. So here, let us review some terminology. If I say what you see on the board R sub 1, what do you say? You say R sub 1 is a relation on A. It means R1 is a subset of what? That was the meaning. But don't get confused here. The R that I am defining is not a relation on this given A. A is given, but R is not a relation on A. If R was a relation on A, if I want to find it, I have to imagine A by A. But R is a relation on A times A. So just by this sentence, which one? This one is wrong, correct or wrong? This is wrong. So can you fix it? So this one was wrong because this means R is a relation on A. But according to the problem, R is a relation on A cross A. Yes?
So it's a square x a square, right? The relation is on.
Why X? No.
Oh, a square.
A squared, so you can say A cross A,
And then
cross A cross A.
Yeah, that's what I meant, sorry.
Okay? Or in other words, you can say R is a relation of A squared, which you can write it as A squared squared, but don't write it A to power 4. Yes? A to power 4 is also somehow correct because it becomes A cross A cross A cross A, but don't write it, okay? I will not use these kinds of notations, but this is the meaning. Understandable? Do you have any problems with this one? R is a relation on a set. It means it is a subset of that set, whatever it is, multiplied by the set itself. Is that clear? Now, because it becomes a very huge writing down, you know, so what I have to do first, I want to explicitly write all elements on R. But before that, I need to find A cross A cross A cross A. So it means that I need A cross A in place first. So we can do it very easily, 1 and 2. So it becomes what? 1 and 1, 1 and 2, 2 and 1, 2 and 2. Do you agree with me or not? This is A cross A. But A cross A cross A cross A, how many elements you expect here now? 1, 2, 3, 4, 16. But 16, can you write 1 or 2 of them for me? It is an ordered pair.
Yeah, but it's 1, 1, comma,
But
1,
the
1.
first one is coming from this one itself. So it becomes what? For example, 1, 1, and this which one? 1, 1. Do you agree? This is one of the elements. And then give me another one, for example. 1, 1, and I don't know, 1, 2. Do you see what I'm doing? And then I can continue. If I want to keep the order, what will be the last one? The last one will be 2, 2, 2, 2. Something like this. Is that clear? But now, can you help me to write some of these elements? So now, because the problem is asking you, write R by explicitly mentioning elements in it. So, and they have told you how to choose. You choose this if and only if this number plus the last one is less than or equal to the sum of the middle ones. Yes? So I am asking you, do you think this is allowed to go inside R or not?
Yes.
Why? Because this means what? This means 1, 1, R 1, 1. Do you agree? This means this. Is it true or false? The first one plus the last one is 2. The middle ones are also 2. So 2 is less than or equal to 2. True or false? False. That's true. So I will let it in. So I will let this one in. Yes? And then, for example, what do you think about this one?
No.
No. Why? Because the first one plus this one is 3, but the sum of the middle ones is 2. 3 is less than or equal to 2 is false. So this will not be allowed to go to my R. Is that right? That's it. I just wanted to tell you. So you can sit down and just write it down one by one. Any questions regarding this? Okay. So now let us go to the next one, which is the most important one actually. We are not interested in all possible relations. We are only interested in a very particular case of relations, which are called equivalence relations. Okay. So let me immediately read it for you. So if I give you a set A, let A be a set, a relation, and usually this is very common in algebra, instead of denoting relations with capital letter R, they show it by this symbol. Okay, tilde. So a relation tilde on A is said to be an equivalence relation on A if you have to remember these properties. If this relation enjoys three properties. For every element that you choose from your original set A, that element is in relation with itself. X is related to X. Is that right? This is called reflexivity, or being reflexive. I have written the words down there. So this is reflexivity, reflexive. The second one is symmetric. What does it mean? It means that if you choose any pair x, y in A and you see with your eyes that x is related to y, then you can also see y is related to x. Okay? And the other one is called transitivity. If you pick three elements x, y, and z, any three elements in A, such that x is related to y, but y is related to z, then these together imply that x is also related to z. Okay? If a relation has all these properties simultaneously, we call it an equivalence relation. Yes? Is that clear? Okay. So let me explain it here on the board. So for example, let me give you one very simple example. So let us take my set. Let me take the set of real numbers. And I define this relation on R by this symbol. For every x and y in R, I define x is related to y if and only if x is equal to y. So in other words, my relation is equality relation. So I am telling you that two elements chosen from the set of real numbers are related if and only if they are equal. Is that right? Now my question is that, do you think this relation that I have defined in this way is an equivalence relation on R or not?
Yes.
Let us check. In order to see if it is an equivalence relation or not, I have to check three things. I have to pick one element from R and ask myself, this is true or false? Okay? If I pick an element from R, is this true or false? I have to translate it according to the problem. This is, according to the problem, equivalent to write as x equals to x. Is this true or false? True. And this is equivalent to this, so this one is also true. No matter what x I choose, any x that I choose from my set, it is related to itself because relation here is defined to be equality. In other words, every number is equal to itself. Yes? Do you think this relation is symmetric? How you need to think. X is related to y. I want to make sure that this is true, that y is also related to x for every x and y in R. Is this true or not? Because when you say x is related to y, in this problem, relation means equality. You know that if x is equal to y, then you can say that y is also equal to x. And y equals to x means y is in relation with x. So it is symmetric. Yes? Here actually we have equivalency. All of them are equivalency actually. But you don't need to write all of it because we want to go from this to that. So you don't need to emphasize on the directions. You have to start from this and conclude the right. Okay, do you think it is also, this is symmetric, so it is symmetric. Is it transitive? Just intuitively, what does it mean? It means x is related to y, means they are equal. Y is related to z, y and z are equal. Can I conclude that x and z are related? Of course, yes. Yeah, is that clear? For example, one of the relations is that in this, let us say we have a school and it has some classrooms. something like that. And then being a classmate on the set of people, students in a school. Being classmate is also considered to be an equivalence class. Of course, the first one is a little bit counterintuitive, meaning that you and yourself are classmates, if we accept that. So everyone is in the same classroom as himself or herself. Okay? If person A is classmate of person B is also classmate to person A. So it is symmetric. If person A is a classmate of person B and person B is a classmate of person C, it means person A is also a classmate of person C. So being a classmate is an equivalence relation. Yes? Is that clear? Understandable? Okay, so the idea is that because the idea behind this concept was mathematicians, they didn't, because equality is very strict. Two things are equal if they are more or less identical. If they differ a little bit, the relation is gone. Okay? But sometimes we don't need that strictness in mathematics. We want to see them as a group, even though they are not identical, but they have something in common. And that something in common is the relation that we want to focus on. Yes? So for example, if KTH wants to organize a classroom for you, they don't know which person is in this classroom. So they arrange something for the whole group. Yes? Because for them to design something for the exam or something, they don't exactly need to know every individual completely. So they want to. So in principle, something like this. If I have this set, if I insist to work only with this relation equality, then I have to think everyone as individual things. Yes? So it means that if I have a glasses, I mean, something like this, how do you draw? Okay? And it is written equality. So if I have that eyeglasses here, I will see only individuals. If they differ by some very small thing, I see them as two things, not one thing. Okay? But if you have this equivalence relation eyeglasses, if I have that eyeglasses of mine, when I look here, I see them as clusters with the common property. So might be some group have some property. I will not be able to recognize them. I will see them as one cluster. And then if I see somewhere else, I see another cluster. So I will not be able to see what is inside. I see them as clusters. This is the way that, so if you insist to work with equality, of course it is very ideal, but of course you have to have a lot of trouble. Okay, but if you take your glasses out and then put this in, you will have. So it means what? It means that now if I take the glasses of this one and look here, what do I see? I do not see inside. Yes? And then I see two clusters. But for me, clusters are atoms. Yes? If I have this, I can go within the atoms and I can see the ingredients. But if I put this one here, this is my atoms. Yes? That's something like, these will be my points. So that's the idea behind this equivalence class. So for example, being a sister of another person, do you think sistership is symmetric or not? Why not?
You're not your own sister.
No, that is reflexive. I'm asking about symmetric property. Is it symmetric?
Yes.
Yes or no? This is your common mistake. That's why I just want to. It's not true because that person might be the brother of the other. Yes. So sistership is not symmetric. Something like that. Okay, so we go to the next one. This is one of the practical problems. This is something you need to know in abstract algebra. I have given you a relation on a set. So remember, whenever you talk about a relation, you should have a set in order first. In this case, I have given you this set equals to the interval from 0 to pi, 0 included, 2 pi excluded. And I have defined a relation tilde on A. Okay? So what does it mean? It means that in my head, I have done the cross product of A and A, and I have picked all elements with the property that I am emphasizing. I am saying that X, so for all X and Y where in A, I myself define the relation between X and Y to fulfilling this equality. Yes? For example, do you think this is correct or not? So, do you think 0, 0 is in my relation? Do you think 0, 0 is in my relation? First of all, 0 should come from my set, but if I put 0 and 0, it is correct, because it becomes sine of 0 to power 2 plus cosine of 0 to, so it means 0, 0 is there. So do you understand what we are doing? So here, we want to show that this definition defines an equivalence relation. So I have to check that this is reflexive, this is symmetric, and this is transitive. Okay, so reflexivity. How should I prove the reflexivity? I would say let X belongs to A. We show that X is in relation with itself. But then this is a very good way of writing. How can I translate this? X is in relation with X. Means is equivalency. Sine X squared plus cosine X squared is 1. Do you see that? Because I have replaced Y with X again. But now, is this true or false? This is a very established identity in trigonometry, so it is true. But because they are equivalent, if this is true, this one is also true, so we are done. Reflexivity is done. Yes? So, symmetry. Symmetry. How can I prove symmetry? I would say let X and Y belong to A such that, help me, such that what? Such that X is related to Y. We show that, yes, we show that Y is related to X. Okay? You are telling me that X is related to Y. So what can I conclude? Even though it is equivalent, I don't need to write equivalency here because I want to go in this direction. So X is related to Y. What can I conclude? I can conclude that sine X squared plus cosine Y squared is 1. Yes? But you can go to a scratch paper. Your goal is to prove this. When you want to prove this, it means the role, you need to come up with which identity. So you go to a scratch paper. This is important. You go to a scratch paper and translate it for yourself in a scratch paper. What is that? Sine of, what should I write? Sine of Y squared plus cosine of X squared is 1. So you go to a scratch paper, you understand this is what you want to prove. And then you have an idea, you come back to the paper, and you know what to do now. Here, what I want to prove is involved with sine Y and cosine X, but I have it the other way around. So it tells me what to do. I need to change X, I need to change sine to cosine, cosine to sine. And if you think in that way, it's extremely simple. What should I write? Instead of sine, I would write 1 minus cosine X squared. And instead of this one, I write what? Go to 1. And then I start simplifying it. So 1 and 1 becomes 2 minus sine squared Y minus cosine Y squared is equal to 1. And then you see that I move 2 to the other side. It becomes minus 1 multiplied by a minus. And, oh, sorry. This is cosine X. And then I get my result. Is that right? And then at the end, you need to write what? that clear? Okay, and then finally transitivity. So what should I write for transitivity? I would write let x, y, and z be in A such that, help me, what should I write? Such that x relates to y, and, very good, y relates to z. We show that, that's good. We show that, thank you. X relates to z. Okay? So then you start. You say that you told me y is related to that. Let me use this symbol. This symbol means and. Y is related to z. So this means that instead of this one, I can say sine. So if you want, let me write it in this way. X is related to y. I can imply that sine of the first one squared plus cosine of the second one squared is 1. But you also told me and y is related to z, translated to the language of mathematics, so in the language of the problem. So this means sine of the first one squared plus the cosine of the second one squared is equal to 1. Okay? And I want to manipulate it so that at the end of the day, I get this. Okay? So again, I would recommend you go to a scratch paper. This is the mindset. If it is easy, don't do that. But I want to prove that x is related to z. What should I prove? I have to prove that sine of the first one squared plus cosine of the second one squared should be 1. This is what I want to prove. So in principle, it is telling me I have to get rid of y. So I have to get rid of y. So if you know what to do, then you can do the algebra, so you can manipulate it. So can you tell me what should I do? Because now I know my goal. To reach this goal, I have to confirm this equality is true. And then what I see y is not even there. So it tells me get rid of y. So but then that is up to you how you want to get rid of y. So which one is better to get rid of y here?
First equation plus.
Plus is better. Yes? If I add them side by side, what will happen? This becomes sine x squared. These two will be added, becomes 1. And these two, this one will be also added. But what do I have on the right side? 1 plus 1. But now this 1 and that 1 are cancelled. And then I get sine x squared plus cosine z squared is equal to 1. And then this means x is related to c. Yes? So this is a typical one. And I want you to do these checkpoints. We have a lot of checkpoints here. Yeah, these are good exercises. You can sit down and do that yourself. But this one, let me stop here because we have only 2 minutes left. And I think this is not some... I mean, I just want to tell you what is equivalence class. Equivalence class are these clusters. So when we have an equivalence relation in place, I told you that you have these eyeglasses on your eyes. You cannot see the individual atoms. You can see the clusters. Those clusters are called equivalence classes. Is that clear? Or we will do it tomorrow. Any questions? Thank you very much. Thank you.